and then you provide a partition to a first-order function. And map, for instance, is a contract, so it really tells you how the data is partitioned in our context, which says that all pairs are independently processed, right? That's really what a map operation does. It's the brain-dead, most simple way of doing parallelization. You can send everything, if you have as many nodes as you have data, you can do a massive scale out, send everything to a different node. That's what a map operation does. So basically a map contract specifies that anything that you can call that function as parallel as you want, basically, right? Anything can be processed independently. Reduce is a little bit more complicated. Reduce is a contract that says that pairs with an identical key are grouped. And the groups, again, can be independently processed. So overall, this model of parallelization, or this data model that we're operating on here, is a key value data model, which is just like the model that key value stores or systems like Hadoop here use. And map and reduce really just one-to-one map to what Hadoop does. Now the observation is, though, that, as I already said, map and reduce alone are not really enough in order to do complex operations like joins or those time series analysis. So generalizing that means we have to come up with this notion of parallelization contracts, which formally are second-order functions that define the properties on the input and the output data of its associated first-order functions. So there is an input contract, which basically says how the data is shipped to the function independently in groups or whatnot. And then there is a first-order function that's then being executed on those groups, and there is the output contract. So the output contract then specifies some interesting properties that people here that work in the DB2 optimizer, that you probably also see some similarity to the interesting properties that we have in query optimization. So that means input contracts really say how are those subsets generated that are independently processable, and that generalizes really map and reduce, and those properties are enforced by the system just through those functions. The output contract then describe the properties of the output of the first-order function. Those are really optional, but if you give them as an additional parameter to the function, then they can be used for optimization, and those have to be actually guaranteed by the user. So you have to make a promise here, a commitment in the function. That's really based on, I'm not sure if any of you are familiar with a programming model that has been developed in Switzerland by Bertrand Meyer, which is called programming by contract. And there was a programming language called Eiffel that actually advocated that. So that's really the main motivation for this work here. If you wish, we are heavily influenced here on that side by the Eiffel programming language. And again, we are working on a key value data model. So what are pacts beyond map and reduce? Just giving you a couple of examples. Those are still, in my opinion, rather boring examples in the sense that they help to realize operation of the relational algebra. So they are very familiar to us database folks. But nevertheless, they also give you a flavor of the contract, and more importantly, those are functions that are missing in Hadoop and cause a lot of trouble because of that. So one function is cross, which of course is a bad function. We can think why, right? Because cross really does a Cartesian product. So it builds a Cartesian product of the inputs, so it has multiple inputs. So it's a very big difference to traditional map and reduce, where you always have a single input stream. Here you have multiple inputs. And the cross contract says that all combinations are generated and will be processed independently. That's what a cross contract will state. The match contract is a contract that will be used to do a equijoin. So the match contract will say, again, we have multiple inputs, and all combinations of pairs with an identical key of all inputs are being built. And again, the processing takes place independently. So this could be an equijoin, right? You could think of it roughly as an equijoin. But the important thing is, this is not a relational operation. This is a contract that tells you something about the partitioning. So it's very important to distinguish that, because it's exploited in a very different way than how you would actually exploit the operators in the query plan. And the observation is that they all take as an argument a first-order function, and this first-order function could do what it wants. So basically, you can implement a join with it. You can implement the Cartesian product, but you could also do something very different, right? So cogroup is another contract that's interesting. So it again has multiple inputs, and pairs with identical key are grouped together for each input, and the groups are processed together. So this is another way of doing joins. You could try to do outer joins like that, but you can also do other operations. But again, the important thing is it's a contract how the data arrives at the first order function. So those are contracts, and those are the contracts that I focus on in this talk, we are actually currently looking for those applications that I showed you into some more complex contracts. So there's contracts, for instance, if you want to do time series analysis, you have to subdivide the data if you want to parallelize that into overlapping subsets. So it's not really a full partitioning anymore. So you actually want to replicate part of the data. So you can define contracts that have some sort of replication in that sense. There's some aspects of that are actually well known in the functional programming community. Again, they actually have done similar things when you do matrix multiplications, for instance. Because if you do matrix multiplication, what you need to do is you have a certain row in a certain column, and you go over all those values, and you do that independently again for everything in the matrix, right? So that means you have this row in this column, and you put it to this compute node, this other row in this column to that compute node. So it's a partitioning in a overlapping fashion, and those are called, for instance, torus functions. Because they actually, when you visualize partitioning, it would look like a torus or donut kind of way how the data is spread. So those are other kind of contracts. Just to give an intuition, there's more than just those. But in the work that we have done so far in the initial year, we just figured we'll look at somehow being able to at least run something like relational algebra plus some extra operation, and those contracts seem to be the most crucial ones for that. So just to give an example how those contracts are used at work, basically here we look at a query which is a TPCH aggregation query, and I'm sure many of you know which query that is. So this query here, it's just a slight modification of that of the Q3, I think. And when we look at that query, how would that be specified using those contracts, right? That kind of almost looks like a query plan, where some of the implementation of the first order functions will do the logic like filtering over them. So first, we have to read from the distributed file system the input O in this case, right? The orders, and then we do a map, and the map is the contract that says we can independently parallelize filter and projection. And then we have to assign the key. So that's really the first order function that is associated with the map contract.